All right, I want to make three comments. So first about the thresholding, I want to say a little bit uh, from a different angle. So I think a couple of years ago, I wrote a blog post to make the argument about to promote transparent thresholding. So I want to say a little bit more using this slide, right? So currently the dominant approach is you have to show the surviving clusters with a boundary, clear boundary. Personally, I prefer the one in the middle. I don't want that boundary. Why? That boundary, I mean, as a statistician, I feel a little bit strange to say this. The field is dictated by statistical results fully, right? So when we present the results, we fully rely on the statistical values. There's no prior information like domain knowledge is involved, engaged in this reporting process. That's problematic. Why? Because what's the cluster boundary? Whatever we decide, what method you adopt to define the boundaries. It's purely based on the so-called the adjustment method. That is arbitrary to some extent, right? There are many factors that don't want to name them, but regardless of what you use in the end, okay, so one argument is that penalty is heavy, excessively heavy. Why? Because when we build the model, we fully ignore the cross-brain information, shared information, and we ignore the neighboring voxel relatedness. So in the end, afterward, we sort of like put a band-aid, try to patch it up, but that patching process is excessive. So that's one perspective. Another argument is that, okay, in the end, we fully rely on the statistical results, but does that boundary has any neurological meaning? Does it? So that's another issue, right? So that's why I prefer without that boundary. So regardless whether like even the blue regions, you can still talk about if you have prior information, previous study to show those regions, that will provide another layer of information. So we don't fully rely on the statistic to make a decision. So it's not a decision process. So that's why I personally prefer the middle one. But I mean, in the field, okay, people still feel I even refuse to use the word significance. So, but the field, that's what we have to face the reality. So the compromise is we can reach that compromise with the right image. So the problem to me, the fully rely on statistics, it's like the tail wag the dog. But in the field, we do have domain knowledge. That's the part we're currently missing. So if you are interested in the blog post, it's on the Avni website. So that's you can read this if you're interested. So there one big pushback I think I heard is that in this post that suggests that I don't even want to use the threshold to define the cluster is because since there are some extent arbitrary, right? So that's the problem. So I suggest to use, for example, 20 voxels as your threshold, p-value of 0.01, for example, voxel level. Some people pushing back say that is stringent enough. Okay, you can do that versus your approach using p-value 0.01 and cluster whatever million cluster, you will end up with a similar pattern, right? So then in the end, you draw this boundary. What does those boundary do, right? So the boundary basically is to some extent arbitrary, and it doesn't carry much neurological meaning anyway. So that's one first comment. The second comment I want to say a little bit about experiment design. So Rick didn't have time to show to compute the design efficiency, right? So is that step necessary? Probably not that big a deal. So as long as you randomize enough, I think probably most of the designs will end up fine. Why do I say that? Okay, even if you run, for example, 1,000 separate designs, then you compare their efficiency. If you take a close look, the efficiency across those 1,000 different designs are pretty tiny. Even if you choose the top one, the first one, right? So in reality, this is a simulated one. The real data sets, you are going to censor some time points. You are going to include head motion components. Once you take those consideration, the subtle differences in terms of the simulated efficiency is probably not really that accurate. So to emphasize another point, if you recruit 100 participants, I just randomly pick 100 separate designs, probably not good enough. Even if you compare the efficiency, just pick the top 100. That's probably fine too. So that's my second. The third, last comment is about, I want to say, complement a little bit more what I said earlier. Someone asked about pre-whitening for wasting state. So does that argument apply to task-based fMRI data, right? So why do we handle I mean, we have the pre-whitening step. In fMRI, we use the 3D Raman fit, right? So the extra step in addition to 3D convolve. So is that an issue for task-based fMRI as well? Well, there's a big difference between task-based fMRI and the recent state. Is that for task experiments, we do have manipulations. That make a huge difference. Why? Because the recent state is a free will process. There's no manipulation. So in the end, we cannot separate which part is the signal, which part is in this noise we are concerned about, right? So there are two big sources for recent state. One is related to the reactivity, right? That part, we don't want to remove the temporal correlation structure. But there's another part which is, for example, scanner noise, thermal noise, or can be a physiological, like a breathing, heartbeat, that it may also embedded in the fMRI signal. So there's no way for us to separate the two in the end. If we want to pre-write the data, then we may remove the part that is related to what we are interested in, which is the reactivity related temporal structure. But for task fMRI, it's different. Why it's different? Well, for task, if we adopt the canonical HRF, so the temporal structure is already embedded in your regressor, right? But even that is still a little bit problematic. So whatever left in the residuals can be part of well noise or physiologically signal part, but it can be also well signal. That it can be, for example, currently regardless of what we use, canonical HRF or even we estimate the HRF, still something we are not doing a good job, which is cross-trial variability. Right? So that's the canonical HRF, even estimate HRF, we still assume cross trials, they have the exactly same response magnitude. So that part is not modeled. That will also cause some temporal structure. That part is currently fine because we don't, most of the time, we don't care about the cross trial variability except for scenarios such as you want to estimate the trial level border response. In that case, it's a little bit challenging. All right, so that's something I mean, those three comments. Now let's switch to the hands-on session. Okay. So that the PDF in the handouts directory is FNE 35. So for this session, so it's hands-on. The data, the directory is FNE data 6, right? So that's pretty much all we for our hands-on demo is located. So in this case, we use the group on cases. So on my terminal, so this is in my case like this. So FNE data 6 group on cases. So if you see what's inside that directory, there's 7 subdirectories. So we're going to not all of them, but probably a few. Depends on how much time we have. So let me go back to handouts. So that's where the demo examples we're going to use. Then One thing about some of the Affinity programs, mostly at the group level, those programs using R. So R is a programming language. Uh, there are few R packages that we need to install. So presumably, when you install your Affinity, then they should be already there on your computer. So there are command line that how do you install those R packages? Uh, Depends on you install one particular one or all of them. Alternatively, you can start R at the terminal, just type the single letter R. You can use this command, install.packages, to install one or more package, R packages. This slide basically is the same as I showed earlier during the group analysis talk. Those are the list of the Affinity programs. So you can always refer to that to find the one that fits your purpose. So as usual in Affinity, we use scripting to provide the information to specify, the input file and what kind of effects you want to extract out of the modeling process. So here it shows the example using 3D MVM. Remember, this program is usually used for ANOVA and COVA type of analysis. For the factors, you can have both between or within factors, and you can also include the quantity variables. But one limitation about this program is there are two, I think. One is it cannot handle within individual quantity variable. Suppose like some ranking, suppose you have a factor within individual factor, like happy, sad, neutral. If each of the factor level has a unique quantitative value, then that would be considered within individual quantity variable. So this program, 3D MVM, would not be able to handle. But you can use 3D LMER and 3D GLMM can handle that. So that's one case. Another thing is a big disadvantage. It cannot handle missing data. So suppose we still use the within individual factor of happy, sad, and neutral as an example. Suppose one or a few participants didn't have, for some reason, have a happy condition result. So that we would have missing data. So those participants would have to be removed if we have to use 3D M, but we don't have to. We can use 3D MER to handle missing data. So that's a little bit about this particular program. The next one, I want to refresh our memory about the R notation, about model specification. So we're using the R notation. So A star B, suppose we have two variables, can be factors or a quantity variable. We use the star to code for their main effects, intercept plus their interaction. So the interaction is coded with a colon. So that's at the population level, at the group level. Then at the lower level, we have so-called random effects. Right? So this is a typical one. I have each participant, each individual has a unique intercept. Then you may have each individual have a particular factor level. You may also have a unique intercept, etc., etc. There's a blog post about 3D MER, so how to specify the model. So there's some tutorial so that you can refer to that. There's a link, web link. You can go there to take a look. There's also, Justin earlier showed how to probably this is a little bit outdated. There are a couple of other ways to help you to detect some of the issues about the data table particularly. So this briefly we review a little bit again about the data table. So data table is basically comes from the notion of long format in R. So there's also wide format. That's probably you are familiar with other, R. Those are the two major formats about it when we create a table. So wide format, that means each row for FMI data at the group level is usually corresponds to one particular three-dimensional data set as the input, right? So for example, suppose we have a factor three levels, happy, sad, and neutral. So for each participant, we need to put it three rows, right? So that, I mean, you could put a wide format, but in currently, we adopt the case, we use a long format. So that's easier to list the information. That the reason is that if from modeling perspective, the format is more accommodative. So in that case, for all the FNE programs, the first column is always the subject ID. Last column is always the input file. For the input file, then in between, we list all the potential experimental variables, and some of them can be covariates. You don't have to, you may create a table that may contain variables that you will not be used in the model specification, which is fine, because as long as the table has the variables available, which is fine. You may have one table can be used for different models. Then if you provide the table directly as part of the script, as the typical convention, we need to put a backslash at the end of each row, including the data table. But if we put a table as a standalone file, in that case, in that file, data table file, the backslash is not required. Okay. Also, the subrick specification, in FNE, we use the square brackets to specify each three-dimensional volume, right? Remember, at the individual level, from out of a 3D Caval or 3D Wimmer fit, you may have, I mean, the output is usually four-dimensional. The fourth dimension can be beta value, many beta values, and the statistic values. So we need to extract. Of course, you can separate them, right? So you only extract one particular three-dimensional data set, but you don't have to. So you can provide the four-dimensional data set as input as long as you specify the specific subrick. That subrick, you can use index, use the number from 0 to whatever number that particular three-dimensional data set, or you can use the label. So in this case, I put a positive, right? So the beta value, so it's always attached with this underscore coefficient. So I usually recommend using the label instead of the index. The reason is the index can be different across participants. That's one problem, I mean, a potential risk. Another is the label is more informative, right? So it indicates what exactly, because here the positive POS is what you provided when you run 3D Caval. You specified based on the task condition. So that's more informative, more and less error prone. I mean, more error prone. So that's about the data table. So that's I think we're ready to demo or to run some of the examples. So we go to the directory. So as I said, there are 7 directories. So I want to go to the 7th one because that may take some time. And in case you have some installation issue, this will pop out. Actually, so once you go to that directory, so let's list the file we have here. We're going to, I think we're going to run this one, right? I will explain what this is later, but so the way you run, I mean, you can exclude the whether I'm using T shell, so I type TSSH, then that command line. So you can return. I mean, it's or you can pipe. I mean, you can save that as for example, I could run RBA2. I can call it a log. So that's in case there's some error message or what the progression, then you can put there, then put a ampersand at the end. So I can continue use the terminal. It will run in the background. So do that. I'm not going to run. So since since I will, if I do, then I will keep my computer busy. Will heat up maybe. So you do that. Say if it runs, in case there's some issue, some R packages, then probably will show up. So we'll let it run. If they're running fine, then just leave it run in the background. So we'll continue discuss later, and we'll come back to this example later. So this is basically about the hierarchical modeling with 21 RIs I mentioned earlier this morning. So it's using the Bayesian modeling approach. So that this would uh, provides a different way to handle multiple comparison issue. So let's if everyone is running fine, so I will start the first case. Let me see if any issues. Oh, you can um, because there's a conflict that exists, you can remove those files. I have those files too. Uh, let's do this before. Let me remove results. So you can remove all of them. So in case you cannot run, well, this is once you move, you're going to lose it actually. So you can remove, then that will void. I mean, we will not have the error message. So we move those files because the output files are already in the directory. So there's no package called data table. I'm not aware we need data table. Let me see. Let me see if I can. No, it's not our package. Well, why not clear to me the data table? I don't even have. I'm not aware data table is a.
Data table is now used by all of the programs to test the format of the input data table that Justin was showing.
I see. Huh. Yeah, the BRMS that you definitely need to install that package. The someone have the JP has that error message, so that in that case it's a requirement. So you need to install that R package. I don't have data table. Is that why I can? Let me see. Oh, I do. I do have data table. Looks like. Okay, I need to put quotes to show that. So for those have error message, you can use this command, or I mean, since I'm in R, you can use this. Then data table, you can use this command. Let me maybe raise up a little bit. Okay, so you can use that command. That should be pretty quick. Take probably a few seconds should be able to. I can do it. Uh, so since I'm doing it R, so I need to select one of the repository centers. So, for example, I choose Pennsylvania. Any of them would work. So install. So it's just 1 second. You would be able to install that R package. Okay. Okay. So I think for those have missing a data table package, you can install, and hopefully that should resolve the issue. For the person who has the missing BRMS, you can similarly you can use the command if you inside R, just install this BRMS. That will probably take a little bit longer. I don't know how long, 5 minutes. Hopefully not too long. So that will hopefully solve the problem. Okay. So hopefully that will get rid of, solve the issues. Now let's come back to the this case. So the first case is pretty simple. It's I call it one way within individual ANOVA with the missing data. That's the only sticky point. So so you can open another terminal. So leave that one, the RBA, that one, the seventh one alone, then open a different terminal, then go to the first one. So this, you can run, which script? Let me see. LMER1. So again, you can type, I'm using tcshell, and do this. You can save that as log file. You don't have to, but you will dump. If you don't, they will dump some of the information on the screen on the terminal. So, but I will explain first what this is, this case. So it's I call it one way within, within individual ANOVA. So what is that case? So there's MEG data, not FMI. MEG, it's at the group level, it's not that different. So it's a one, we don't have to talk about the detail, the background information. So there are 17 participants, 3 conditions, baseline, then ketamine. So that's then a placebo drug, a placebo. So 3 conditions. That means each participant was scanned 3 times, 3 different sessions, right? So it's under baseline condition before taking the drug, or then there's a ketamine, there's a placebo. So those. But for some reason, some of the participants didn't have some of 1 or 2 of the conditions. You can say the missingness in the table on the right-hand side on the screen, right? So there's, for example, this subject 111. So this one I will missing data for the placebo, right? Depends which condition, right? So this, if we depends on what kind of modeling strategy we're going to adopt, right? So if we use the traditional studies framework, this is one way within subject ANOVA. That means we would not be able to accommodate all the participants, because especially for those without with missing data, we have to exclude them because we use ANOVA framework, right? For example, using 3D MVM. So that's one way within individual ANOVA. Then we would exclude 6, so we would be only able to use 11 participants. So that's the straightforward approach, but we're going to losing quite a number of participants. Second approach depends on what you want to focus on. We want to do pairwise comparison. Suppose that's probably typical case. Want to compare, for example, ketamine versus baseline, or ketamine versus placebo. So those are probably the reasonable comparisons. If we do that, we're not going to lose all of them. Depends on which pairs. For example, if we want to compare ketamine versus baseline, so that means we focus on the first two columns, then we're going to lose, for example, two participants. If it's ketamine versus placebo, we're going to lose probably 5 of them. I don't remember. 1, 2, 3, 4, four of them. So that's a better approach compared to the ANOVA, right? Lastly, the third method is that we use all of the data available. Then we use 3D-MER. That because that we use a hierarchical modeling. That business is not a big deal, except as long as we're comfortable to make assumption. What is that assumption? That assumption is the reason the data, those participants didn't have those conditions available is a totally random. The reason has nothing to do with those tasks. Is, for example, one particular participant because I have scheduled for something else that they couldn't attend the scanning. So that has nothing about the brain response. For example, is another reason is because the person is sick. Well, is sick. That sickness is related to the medicine, or is unrelated. That depends. So it's related to the medicine. Then that's a little bit problematic. But what can we do? Well, we can't do much, right? But at least that's something a little bit tricky. We don't have a solution to it. But anyway, so back to this scenario. So the best case is use 3D-MER as long as the assumption is reasonable. The business is random, totally random. So let's go back to this terminal. So I assume everyone has already got the result in this case, right? So this is a full brain, but the voxel level results should be, because the voxel size is big, the resolution is low. So you should have the output. It's called a result.rmer plus telarec. And there's a head and there's a break file. So we could take a look. What time should we stop here? I forget. To take a break.
You have until maybe 10 more minutes?
Huh? I'm sorry?
Maybe 10 more minutes?
Okay, 10 minutes. Okay. So we have the result. We can briefly take a look. So this is just a routine for us now. We don't have an anatomic data set in this case. We just, it's put 3D-MER as underlay. Both the output for both the underlay and the overlay, right? So then you can set the threshold. For example, depends on where. We just as an extra we put pointed, for example, 0.02, and there's a shortcut you can specify the p-value. So once you specify p-value, then where's my okay? You can put a box. The alpha, the A button A is the transparent threshold, right? So you can navigate. Well, this is the condition. It's not really interesting. Probably it's actually we want to discuss a little bit about the script itself. I forgot before we visualize the results. So the script is this one. So in the script at the beginning, it shows the data, the missingness, right? So down below is the content of the script. The bottom part is the data table. First column, subject ID, last column, input file. There's only one variable, an experimental variable, which is the 3 conditions, right? Ketamine, placebo, baseline. So data table is straightforward. When we use 3D-MER, we need to specify the model. The model is also pretty simple, right? So it's just one condition, one variable, right? So 3 levels. Then plus, in this case, we'll have the random intercept. there's also, I mean, the intercept at the group level as well. Even though it's not explicit, we could add one for the fixed effects. But the R notation by default, there's always a intercept there. If you don't want the intercept, you can put a zero. That means you don't want the intercept. But that's usually a special case. Usually we don't want the intercept. It's by default it's there. So this is also intercept, but intercept at the individual level. So that's called random effects, and the residuals are already or by default is included in the model. So that's the model specification. Then there are few lines. I mean, less few lines using the GOT code to specify the effects we want to estimate. Right. So for example, here is ketamine versus placebo as a second one. I mean, some of them probably don't make sense. For example, the third one is ketamine minus placebo minus baseline, probably doesn't make sense, but it's just as a demonstration, I mean, show different sorts of linear combination of effect estimation. So let me go back to the visualization part. So the first is a single condition. That's probably not interesting. We can switch to, for example, comparison between ketamine versus the placebo, right? So then the overlay, we choose the effect estimate. The threshold using the Z statistic. You would think this would be T, right? So that's a traditional, I mean, when we do T-test, do ANOVA, a comparison would be T. But for 3D, when using linear mixed effects modeling, we have to use, I mean, a Z value. The reason is that it's a little bit difficult to assign degrees of freedom when we use the linear mixed effects modeling approach. So once I switch to that, there's low clusters. Well, that's because my threshold is too high now. So we need to, for example, pick up, I mean, you decide whatever you want to choose. So you can choose the specific cluster size. You can have cluster size, I mean, 40, probably I'm pretty liberal. I'm not really so picky about the cluster size. So as long as I show some pattern, that's probably good enough for me. So that's for this case. Any questions about this particular case? Whoops. Wrong one.
There's a question in the chat, Gong.
Okay, about approximation about degrees of freedom. Yeah, that is I think that depends on the. Let me see the. It depends on the situation. I think there are multiple ways to estimate degrees, but it's a little bit controversial. I mean, it's not that unless you are so want too precise, but that's probably not worth worry about the degrees of freedom at the group level. I mean, that's the same thing like a multiple comparison, right? Where whether it's the p-value is 0.05 or it's a 0.0523, I mean, it's not precision. It's not really worth it. That's why I prefer, usually I don't use the p-value. Personally, if not for FMI, for example, for behavior data, I prefer to use the point estimate plus the standard error. That's a little bit better to characterize the uncertainty information instead of a p-value. But in FMI, so we'll have to focus on at least for visualization purpose. So, but even for that, that precision is just not worth the effort. I mean, once you take into consideration about multiple comparison, um, that's uh, that's that's what how I considered. There's some errors about the segmentation foot. That a little bit complicated, so I have no idea. Model test failed. That's also, it's probably missing R packages or soon, most likely, because the model itself in this case is, I mean, pretty reasonable. Um, I guess we can stop here since, all right. I want to say a little bit more about the degrees of freedom when we use the R package, RME4. So on this FAQ website by the package maintainer, so they address the issue. So for example, this subsection explains why the degrees of freedom is not available by the package itself. It does have the, if we use another package, then we have a couple of other options, right? So the setter switch and convert Roger, so that's for example. But the problem for the issue is that when I decided to implement the program in 3D MER, well, even currently it's still the case. We need to use for those post hoc estimation, for example, pairwise comparisons, we use the R package PHIA, PHIA, PHIA package. That package does not provide this degrees of freedom assignment. So that's the main reason. All right, let's back to, oops, where are we? Now I think we can discuss the last case. Well, we shift to the last case we run at the beginning. That's the one we start the script at the beginning, right? So before we run even the first case. Let me go back to my slide. So let me explain a little bit. Let me open the script actually. That's probably better interface to explain. One, RPA2. So this is the script. Actually, it doesn't. Well, let me go back to the slide again. So this is the case at group level. There are 124 children. Each of them have some value. They we work on 21 regions of interest. So the Y, the response variable, some Z score. So this is I think it's pretty much like a racing state. They watch a movie, I believe. Then so that's why in the end we have the Z score. That's Fisher Z score converted through the transformation. Then there's a behavior data. That behavior data is TOMI, I think it stands for theory of mind index. So that's so if we analyze each RI separately, this would be a regression, simple regression, where it's A plus BX. So there's one experimental variable. So maybe we should open the data table to see what's the, let me move upward a little bit. So the data table is this, right? So it's this. So you can say first column subject ID. Then there's no input file in this case because it's RI data. right? So then there's a RI. Second column is the RI labels. So there are 21 separate RIs. So then the third column is the score. That's the Y. That's the response variable. It's a Fisher transform R values. So then the fourth column is the total. The total is the total index for the theory of mind. So the last column is the three separate indices. So the total is, I believe, it's the sort of I don't remember exact. It's probably some sort of average across the other three, advanced, basic, and early. So the last three columns is not used. We only use the total. So that's a theory of mind index for each child. So we could analyze this data set for each RI separately, right? So that's basically once, in the end, we want the A plus BX, we're interested in the B, the slope effect. So that's an association between the theory of mind index and the Z-score. We can do that. That's the typical approach. That's pretty much equivalent to a massive univariate. But if we do that, then we are facing the trouble, right? So this is not a voxel level, it's RI. The only available, either we use FDR, first discovery rate, or use Bonferroni, right? Bonferroni probably is the penalty is probably excessively heavy. So probably first discovery rate is probably a little bit less, right? But still, that's still to some extent a little bit excessive. So the better approach is we adopt the hierarchical modeling. So we build a single model with all the 21 RIs incorporated into the model, as I explained earlier this morning. So this was developed probably 2017, quite a few years ago. It's the reason I started with the RI is because of the computational cost. So even this is you probably on your computer probably takes, I don't know, depends on the computation power, maybe 10 minutes, can be 20, depends on number of CPUs and the computational sources available. So you can imagine if we apply this to voxel level, that it would take basically it's, I don't know, number of years for the number of voxels we typically deal with. So that's why we didn't make much progress over the past few years. So only recently there are some advancement because use some technical advantage. So that is will be hopefully available in a few months. So for example, next FNE workshop, hopefully we'll have a program Simba, right? So that we may be able to demonstrate with Hobrian voxel level analysis. I mean, not a voxel level, but to build a single model for all the voxels within the brain, then use a similar modeling strategy to deal with it. But for now, so we are using this RI-based analysis to demonstrate. So hopefully, everyone has managed to have the result. I mean, to run the script. So in the end, it should have a few results. So the major one is this. So that's a text file. So if we can open it, so it will show some primary information. That's probably about the data set, RIs, right? So move downward, then we'll give the single model. You can even say the model, sort of the model formula here. So there's this line, right? So Y equals intercept plus total. Remember, that's the theory of mind index, the quantity variable. Then it's pretty much like a linear mixed effects model, right? So each subject has their own unique intercept. Then each RI. So remember, this is a single model for all the 21 RIs together. So RI, those 21 RIs is pretty much like subjects. We have the random effects. So the random effects both for the intercept and the quantity variable. So to some extent, this would be a linear mixed effects model. But you may wonder, why can't we use for example, LME4, the R package, to handle it, right? It can to maybe approximate it, but it's not flexible enough. Moreover, if we extend this model approach to the whole brain, all the voxels, then the R package is just the dead end. We can't do that. So that's why we adopted the Bayesian approach. Bayesian approach, if you know some extent of that approach, is the one main thing is different from the traditional statistics, the frequentist approach, is that we need to assign prior information. Some people argue that the prior information is, right, it's a little bit subjective. That's the word to describe the Bayesian approach. But the prior information, what do we do is, well, first of all, I mean, in each domain, we probably almost all the time, we do have some prior information. Second of all, that depends on what kind of a prior information we provide. In this case, so the two major prior information is about cross-subject variability and quasi-ROIs. That prior information assumes they follow Gaussian distribution. That is not much different from the traditional model, even for whatever residuals or linear mixed effects model. For cross-subject variability, we, by default, we assume Gaussian distribution. But with the Bayesian, it's not just that, we have more flexibility. For example, if we have outliers, if the distribution we suspect is not symmetric, we have way much more room to provide the prior information. Suppose it is skewed, it's one tail is heavy than the other, is heavier than the other, then we can use many different types of distribution. For example, student T, that's one possibility, or we can use some others, right? So there's so many other skewed distributions. So that's basically the under the hood for this program. So that's the model specification. Once we run, then we'll get a bunch of summarization. We don't need to go through that at the moment. So, but what do we care about is, remember this case, we have 21 ROIs. So at the end of this file, this is a text file, you can see there are 21 rows. Each row shows for each particular ROI. Then there's the information here. So this is the table. The table, first column gives us the average, then standard error. I mean, this is standard deviation. This is not standard error. Unlike the traditional statistic, we have the point estimate, we have the standard error of that estimate. But for Bayesian statistic, we have the called posterior distribution. For each distribution, we can get the mean. It's, for example, Gaussian, we can approximate it as a Gaussian distribution. So we have the mean, and we have standard deviation. That's why the term is not standard error, it's a standard deviation of each posterior distribution. We can also get some other quantities. For example, the rest of them shows the the quantile. So this give us where the 2.5 quantile, 550. That's the current coded profiles. One particular point I want to make about the Bayesian statistics, in the end, unlike traditional statistics, we need, remember that's a null hypothesis significance testing, we pretend there's no effect, right? That's always the condition we start with. So under that condition, then the p-value tells us how surprised we are, right? So if the p-value is small, that means we're very surprised, right? So that p-value tells us about the extent of that surprise. That surprise is conditional on that assumption. The assumption we assume there's no effect. But for Bayesian statistics, we don't have that pretending part. We just directly estimate the posterior distribution. We just directly say what's the probability of my effect lies in whatever the region. So you can pinpoint, for example, the 5% interval, that would be the 2.5 percentile and the 97 97.5, that will give us the interval of that roughly equivalent to the confidence interval in the traditional statistic framework. There's a column called P plus. That basically shows, since the well output is the posterior distribution, so it's a density, it's a curve. That curve presumably is similar to Gaussian distribution. So this P plus give us the area under the curve at the right-hand side of the zero value, right? So later on, I can bring up the slide here. So this 21 regions, we can plot out like this, right? So stack them from bottom up, rank them. So there's a zero value, which is the green vertical line. You probably have in the output, presumably you have this image file. So this tells us about the evidence, this statistic evidence. The error on the curve, that's just the direct estimate where the each region the effect is. In this case, the effect is the slope, the quantity variable, theory of minor index. So the marginal effect. Right? So that's the slope. So that slope for each region, we can say the evidence. From bottom up, you can say the vertical line. If the distribution, for example, the top 1/3 of them, it's most of the, or some of them, almost all of the distribution lies above zero, positive, right? So when we reach to the middle part or the lower, or the rest of it, that becomes a little bit, probably we would think the evidence is either weak, too weak, or there's no evidence at all, pretty much noise, right? So you may wonder, what do we have to make a decision, pick up a p-value of like a traditional p-value 0.05? I mean, statistics, do we have to make a decision? In real life, many scenarios we do, right? So we do need to put a threshold. Even drunk driving, the police stop, the driver, they do have a threshold to judge or the amount of alcohol in the blood. So many scenarios, even the vehicle, the emission test, they need to set a threshold. That threshold is not some arbitrary number. It's based on, some utility, right? So you pass the threshold, then versus below, there's some plus and minuses. You need to balance the two. But for the science, do we have such a utility? Well, to some extent we do, but that it's difficult to quantify, unlike the real life situation. There's some real cost associated with it. But pure science, or at least for FMI, it's difficult for us to quantify the bias, right? So we have both false positives and false negatives. Which is more important? We can't give a concrete number. So what can we do? The best, I think, is just present the full results. For this particular case, in the publication, we'll just show all the 21 RIs like this. Then you can emphasize some of them at the top 1/3, so you pick up them as strong evidence. Leave the rest, in the paper. We don't have to hide them. That's pretty much like the highlight, but don't hide, similar strategy. So that's this program can tell us about what from the Bayesian modeling approach. So down below, there's I mentioned earlier, so there are two modeling approaches we can compare, right? So this Bayesian build a single model versus a traditional using massive univariate, analyze each R separately. We can directly say which model performs better, right? So we can use the model to make some predictions. So that prediction is basically generate new data, simulate data. So the left, the blue one versus the red one, immediately the visual check will tell us. This is called a posterior check. So that's this example. Any questions at this moment? So this program is again available for RI, a bunch of RIs at the moment. Oh, that profile, I think there's R. I don't remember if I put in the affinity distribution. Um, maybe not. I will share that R code so you can use that to generate the plot. Yeah, there's probably I should put it somewhere in affinity distribution so that you can use direct to a. Oh, I forgot to mention. So in this directory, so there's another file. It's pretty big. This one .r data, right? So the before part is just the prefix. That's affinity style. You specify the prefix. Then there's this .text. There's a .r data. This one you can. I mean, if you are familiar with R, you can just launch R, and now you can directly load. I believe that file. You can directly load it into it. Right? Because it's big, loaded. Then once you can, actually, I don't remember what we have here. So the data information is already there. There's also output. Um, let me see. I don't remember what I have. I haven't done this for a while. See, you can use summary, this command, to, I mean, if you're familiar with R, this is the model, basically, the model output object. So this basically shows the overall summarization of the results. But this is not at the R level. So there, if you are familiar with the R package BRMS, so for example, if you load that package, BRMS. So once you load it, then you can do a bunch of manipulation, including to plot out the whatever the those stacked plots. I mean, like this one on the upper right corner, that plot. And you can also generate the posterior check, those two curves, like the one later. There's a commands to direct generate. Since that's why this file, this file, this .r data, so you can do many manipulations and do model quality check as well. So that's why it's saved in each directory. All right. I think that's about this example. Let me go back to, I think we can do one more, which is, let's do this one. Case 3. So it's a four-way ANOVA. This is a real example, but since we're not going to run for all the voxels in the brain, I believe we only focus on 27 voxels in the brain, 3 by 3 by 3. So you may feel a little bit complex, right? So the 4 factors, among those 4 factors, there's a between individual factors a group, young versus old. Then 3 within individual factors. There's first of all, there's task perception versus production. There's a probably linguistic study. There's a syllable is a simple versus complex. There's a sequence, also simple versus complex. Oh, this is nodes. That means it's surface. Looks like, yeah, looks like, I'm not so sure if that's the case. Let me double check. Oh, yes, it is actually. So let's. I'm going to skip this. I'm going to go to the discuss the 5th one. Actually, that's probably more interesting. So this one, it's so at the individual level, estimate the hemodynamic response. This is the exactly one we used in the published paper. So the data information is we have two groups, roughly equal. There are 42 controls, there are 43 bipolar disorder. So I think they are all children. So that's the two groups. Then there's two conditions. The congruent, this is a Franker task, congruent versus incongruent. So two conditions, two groups. If we use the canonical HRF, then this would be a 2x2 ANOVA, or it's a mixed ANOVA, one between subject factor, then within, right? But in this case, we use the attempts, the basis functions to estimate the hemodynamic response. So in this case, we're going to use 13 time points to characterize the profile of hemodynamic response. We're going to use 3D MSS on only those 27 voxels. So let's go to the terminal. So let me move one up. This is the fifth. So under this directory, what's the script? There's only one called say tcsh run ms text. As usual, I put as a log file, then put the ampersand. So since I already have the output file, I'm going to let it run, but I will let you to do that. Hopefully you will not have any issues. This requires the R package, probably MGCV, and the other one is probably GAN4 or something. Yeah, those two are packages. So say if you can run that script, should not take too long, probably a couple of minutes. So in the meantime, let's take a look at the script itself. So inside the script, the header basically describes what we have, right? So 44 controls, 43 patients. Then we estimate the hemodynamic response with 12 time points, two conditions, congruent and incongruent. The TR is 1.25 seconds. 6 is a covariate in this case, only on 27 voxels. So the script is, there's two data tables. The first data table is this ms.tbl. Let's open that. So this first column is always subject ID, last column input file. In between, we have 6 males and females with dummy code in this case. It required actually, unlike 3DM, MVM, 3DM ER, in those cases, factors we don't need to dummy code, but for this case, we do need dummy coding. I usually suggest using ones and minus ones. The reason is that because they're centered. So if we use ones and minus ones, then the effects of interest will be interpreted with the average between the two groups. So that's why we need to dummy code as zeros and ones. If we code as ones and minus ones, if we code as zeros and ones, it's a little bit problematic because the other effects would be associated with the group which coded with 0, right? Which we don't want that. So the reason we do ones and minus 1 because the center value is 0. So the intercept or the other effects would be interpreted as the group average between males and females. So that's a 6 column. The group we also code as ones and minus ones. It's probably not important for the group, but still, it's probably it's convenient coded as centered values, ones and minus ones. So next one is the TR. Right? Remember, basically those are the basis functions, the tens. Right? So we code the zeros, the first one, all the way to 11. So we take 12 points to characterize the profile. So that covers probably 14 seconds because the TR is 1.25 seconds. So that's a data table. Then there's another table. I think it's what do I call? Let me go back to the script. It's this. That's the table for prediction. So in the end, we want to plot out at each voxel the estimated profile, HR, I mean, the hemodynamic response. So in this table, the prediction table, the first column is basically each group. Say there's a control group, CG, then there's a patient group, PG. So for each group, we want to estimate the hemodynamic response, then the TR0. The original TR is 1.25 seconds. So we want a higher resolution. So every a quarter of a second, then we put a higher resolution, put it as a data point. So we still need to put 6 males. We put 0. So now this is important because we dummy code the males and females with zeros, with the ones and minus ones. So now when we estimate the hemodynamic response for each group, we want the value is 0. That doesn't mean the 6 is 0. That means it's basically the average between the two groups. Same now for group, then we need the control group is dummy code at -1. So down below, the patient group is dummy code as 1. So that's why for the other column, for the third column, is the grouping for the patient group and the control. The last is the TR resolution. All right, so that's for the prediction table. So once we run it, you should have the output, right? So I hope everyone would be able to have their output. So there, let me go back to the script again. So once you have the output, there's a few commands. It's a 3D bucket. That program basically extract the output. In the output, there are multiple, I don't remember how many, probably hundreds of subbricks. That's because we have the prediction and also the statistics. So this, just for the visualization purpose, I extract those specific ones. For example, the first one, control group, I extract those subbricks to get the hemodynamic response. So that's, I use this command. You can see output, we have the subbrick selector, the square brackets, from 7th to 95, because the prediction is high resolution. It's every a quarter of a second I get an estimate. So there's a parenthesis 2. That means I want every other subbrick. I don't want every subbrick. Why? Because each beta has a t statistic or statistic value. So we want to skip those statistic value. I only extract those estimated hemodynamic response. So that's for visualization purpose. All right, so that's for each group. I get the estimated and standard error, so you can plot it out later on for visualization or for publication purpose. We have the estimated profile, the hemodynamic profile, but we can use the standard error to put a uncertainty band for each profile. So that's the reason I expect the standard error. Extract the standard error for each profile. So that we do that for each group. So that's why the first 4 rows. The last one, we get the difference between the two groups, group difference. So that's basically all those 6 lines for visualization purpose. Let's take a little bit time to show the result, to visualize the results, right? So again, this is the lecture4 brain. So only 27 voxels for demo purpose. So we don't, underlay, we don't have an atomic structure, right? 27 voxels. It's no there's no point to show that. So we want to load the last one, the result. Well, then load it, that's basically the output. But the output, you can see there's so many, I don't know, probably over, it's out of the scope of the screen to see how total number of subjects, but there are many. But for visualization for overall, suppose we want to look at the group difference in terms of the profile. We choose this one, that's a threshold, that's a statistic. Oh, sorry, that's wrong. I mean, this should be the overlay should choose that. Then this threshold we should use. I'm a little bit confused. Oh, okay. There's no estimate because this is about the overall. So this overlay or threshold should use one single. That's just a statistic value. Probably I believe this is a chi-square with a 2 degrees of freedom. It's just for visualization purpose. If we move the threshold all the way up, so the p-value, well, depends. This is not for brain. There's no pattern to see, so that's not really interesting. But at least it shows the p-value or p-value here for each voxel, right? But the point here is a lot about it to show the overall pattern in the brain. I mean, if we have the whole brain available, yes, we can do that. But here, the reason here is I want to show to visualize the estimated hemodynamic response at the group level. So to do that, to able to do that, we need to change the underlay. For example, we choose the control group, select that as our underlay. If we choose that, well, that will not change anything, right? But that will allow us to click the graph button, right? So is that nice? For each, I mean, for those, this we're showing, I mean, in this case, a sagittal view, show those 9 voxels, they, at the group level, this is the group average, because those are 144 subjects, I believe, well, no, 87 subjects. So that's the group average. Well, that is, well, it's sort of some type of average. So that's estimated hemodynamic response. So there are, I mean, you can use the typical trick, focus on 2 by 2 or just single voxel, depends on what you do, right? So there are a couple of tricks I want to show. Let me move a little bit like this, show different tricks. I believe there's a, oops. So on this graph window, there's this button at the lower right corner called OPT options. So if you click that, there's a pop-up menu. On this menu, click grid, then select the last one, horizontal Z. That, I hope you can see on my screen, there's a horizontal line. That's basically 0. That's the baseline. Right? So that's where the baseline, the 0 is. So in this case, is that the initial dip? I don't know. Maybe just the inaccurate estimate. So you could argue that's it is under initial dip, or it's something capture something unrelated to your activity. So who knows? But at least that gives us some sense where the baseline is. So that's one thing I want to show you. The other one is where the x-axis. How do we load the time? So the time is, I think, 12 TRs. So that's about 13 point something seconds. So how do we show the time where the peak is, for example? I think that we can use choose. I mean, let me go back again so you can see. So click the up button, then this pop-up menu use create grade, then choose. So you can specify, I don't remember, probably let's try 5. So that will give us, I don't remember, this is, I have to do some arithmetic to figure out choose which one. But let me see. I don't remember now exact. So it depends on where you can figure out where's the each vertical line. You can choose the grid size. So then you can pinpoint where the peak is, for example. Those are the couple of options you can use to help you visualize the estimate the hemodynamic response. Okay, so that's nice because it give us some confidence. I mean, the traditional approach, you make an assumption about canonic HRF, we just get a scaling factor. We have to trust the how accurate the profile is. For with this approach, at least we have need to be more confident, right? So we estimate the HRF as long as the profile matches our prior information as the signature shape, right? So it goes up, then we cover, maybe have some undershoot. In this case, the undershoot is pretty large, almost as big as the overshoot, the peak. Right? So either whether that's well or not, I mean, this is just one study, right? Hopefully, as we adopt this approach more and more, hopefully we can find some convergence across different studies to cross validate. So that's the hope. At least this is one way to improve the estimation accuracy and the detection sensitivity. Any questions? I think I'm reached to the end of this session and the end of this boot camp. Right. If no questions, I'm going to stop here and I'd let Paul to say a few words about this boot camp.
All right. Well, thanks for, well, I guess I can turn my camera back on. But that works. Okay. Well, thanks very much, everybody, for attending this boot camp. I think we used to do 5-day boot camps and it was really exhausting. We do 3-day boot camps, and I think it's still quite a lot of information that we cover. So hopefully it's things that you find useful, maybe new ways to think about data or new functionality for things. And I hope we stress throughout the boot camp, one, the importance of visualizing your data and thinking about things. But we're very happy to have further discussions kind of based on this and analysis. And if you find interesting things in your data or things you notice, we're happy to hear about those too. So thank you all very much for attending. We know it's a lot of time out of your week as well, and especially for people in every time zone around who made the effort. Thanks. So hopefully see you around campus, around a conference, or on the message board.